Alright, good morning, welcome. Today is March 19th, day 4 of quarantine. Hopefully everything is going well. We're going to continue our lesson on series and parallel after our virtual lab yesterday. Let's go and start with a quick meme. I found one online. Here we go. How did I feel after after discovering what an electrical circuit was? There you have it. Oh, that's pretty cool. Anyway, series and parallel. Now, if you were not able to answer all the questions in the worksheet yesterday, remember it's this one we're talking about, series and parallel circuits. Let's go over it. So, thanks, Ross. Thanks. So we know what we're doing here. Let's go and draw our circuit first, starting with our battery. Our battery is big line, small line. Big line, small line. And then we have three resistors. Resistor 1. Yes, make sure you follow us so you can chat. And then make sure you subscribe on YouTube also. Scroll down for the YouTube link. Here's resistor 2. And here is resistor 3. Like so. Alright, so let's call this R1, R2, R3. Okay. Alright, so now if you set your values, remember you're supposed to use 5, 10, and 20, and then your battery should have been 3 volts, right? What you should have noticed, a few things, is that the value that you get for the current, whether you're measuring I1 or I2 or I3 or I total, they should be all the same value. Mr. Z, was power different depending on which formula we used for the series circuit? No, but you have to use the correct one, and we'll talk about that. Because the V is not V total, it's not the battery, it's the V of each resistor, which is different. Alright, anyway, so you should have seen that whether you put the ammeter, remember the symbol for ammeter is circle with an A, so that's the ammeter. This is what measures your current, your amp. Whether you put it right here or right here or right here or right here did not matter, because the same flow happens wherever you place it. Alright, and so the other thing is that what you should have noticed is when you're measuring your voltages, your V's, okay, the resistor with the bigger resistance, the 20 ohm resistor, should have dropped more volts, whereas the smaller resistor should have dropped less volts, right? Let's go and pull it up on our FET simulation. FET, Colorado, and then go to physics, circuits, and DC kit. Okay, we wanted one battery, 3 resistors, 2, 3, connect. Alright, and we want conventional current. Okay, now using the multimeter, let's go and set the values. We'll keep this one at 5, this one at 10, this one at 20. Alright, and this is 3 volts. Alright, so of course the 20 will give you 1.171, the 10 will give you less, the 10 will give you less, 86, and of course the 5 would give you the least, 0.43. Alright, now when you want to do R12, or sorry, V12, okay, that's the voltage across 1 and 2, so I have to make contacts. Let's use orange for that. Orange, V12, I have to make contacts at the start of 1 and the end of 2. You can use any formula and it should give you the same value, and we'll go over it in a second. Because all of them have to work. It's not just one or the other. Alright, so when you do V12, you have to touch the front of 1 and the end of 2. If you want to do V13 or V123, 1, 2, and 3, we want to touch the front of 1 and then the end of 3. Okay, which is essentially the whole thing. Alright, so we have R1, R2, R3. For me it was 5, 10. Ooh, how do I get rid of this? I don't know how to do that. Okay. There we go. Pen. 20. R12, okay, is basically using the series rules, and we'll talk about the series rules today. V1 would be the voltage across number 1, and we saw that as 0.43. Boom. 86. And 171. Okay. Current was the same. What was the current? 0.2 or something like that? Well, I can just do it. If you use Ohm's law, you can probably do it. 35 over the total. Oops, 3 over 35. Okay. And what you should notice is that the current is essentially the total voltage V divided by the total resistance R, and that's what the value you're getting when you use your ammeter, right? So if I use my ammeter, first I have to make a cut, and then stick the ammeter there. I want to use wires. I don't have to, but I like using wires. Oops, I missed. Oh, I missed again. There we go. 0.09. 0.09 amps for all of them. Okay. So power equals IV, and you can use I times V. Power is also equal to V squared over R. Power should also be I squared R. So power 1 should be I1 V1 or I1 squared R or R1 or V1 squared over R1. Okay, so do they all give you the same value? Let's take a look. I 0.019 times 0.43, I get 0.0387. Okay, and this should be in watts, capital W. If I did I squared, so that's, what is that, 0.09 squared times R is 5. I get something else. What happened? What happened? Okay, let's take a look at our voltage drops first. 0.43 plus the 0.86, oops, 0.86 plus 0.171, that gives us, oh, 1.71, I messed up. 0.43 plus 0.86 plus 1.71 is our 3 volts. So our voltages work, our current work, our power, I times V, I times V, I times V is what we want to do. so that's 0.00, oops, times 10, 0.1, 1.171, 1.71 times 0.09 is 0.1539. All right. My series ones were different depending on the formula, but the parallel ones all give the same power. Very good. So use I times V. I times V. So P1 is I1 times V1. Like this. Alright. So now we have to analyze what is going on in our series circuit, because I didn't give you any formulas, so we didn't really talk about it. I want you to discover by experimenting. So we're going to use that one. And that is because we have the same current going through. Which means that the bulbs, if these were light bulbs, remember power is similar to, or should be proportional to the brightness of your bulb. The more power equals the more, or the brighter it is. And so when you put light bulbs in series, they have different brightnesses. Okay, the one that has the higher power, when power is higher, so is brightness. And so the powers will be different, and the brightnesses will be different as well. So things to notice: number one, for series circuits, or resistors in series, sorry, I should say that, current is the same. That's because there is only one pathway for the current to take. Okay. Since the current can only come out of the plus end and then go through, the same current has to go through all three, therefore the current through all three resistors is the same. Okay, and it turns out that the resistance kind of adds up. So if you actually try to do this with one resistor or two resistor or three resistor, one at a time, you'll see that you get a different amount of current flowing through in the system. So if I cut this, cut that, take this resistor out, so now we have less resistance in the system. Connect, boom, now we have more current. 0.2 instead of 0.09. Okay. Resistance adds up. Resistance adds linearly, which also means that it doesn't matter which one is first. You just add them up like a scalar quantity. We have this for resistors in series. Okay, Req, rec, is equal to V divided by I. So the total voltage divided by the total current. So the total resistance, Req, is total voltage divided by total current. And if you have two resistors, each resistor will drop its own voltage. Okay, there's a certain amount of volts that you drop for each resistor, and then if you divide by I, remember using Ohm's law, V1 should be I times R1, V2 should be I times R2. You end up with this formula, R1 plus R2. Okay. All right. Now let's make sense of this. So imagine having just two, well, because it's easier to draw two instead of three. The battery is similar to an elevator in that it raises you up in potential. Now we're using gravity as our model. So this is the battery. So if you're on the third voltage floor, you're all the way up here, and the elevator will take you up. Yay, you're a positive charge. That's you. Okay. Each resistor is kind of like steps or staircases. Okay. R1. And by going down the resistor, you've fallen some V amount of volts. Some potential has been lost. And any spot along this line is V1, or the leftover. And if you only have two resistors, then whatever your second resistor is doesn't really matter. Let's see, 2. That second resistor will use up all of it, and then now you're back to 0 volts. Typically, to make it easier, we just set the bottom of the battery as 0 and say that the top of the battery is the positive end for +3 or +1.5, whatever the battery is. There is a way to change the potential value by grounding the connection. If you'd like to learn about grounding, consider taking AP Physics C next year. But this is our second resistor, R2. So in the diagram, in circuit diagram mode, this would be battery, resistor 1, resistor 2. All right. Now, basically, you're going to drop some V1, you're going to drop some V2, and if this was V total, then V total must be equal to V1 plus V2. Okay. So in series, current stays the same. That means I1 equals I2 equals I total. As long as you have only one path. And V, the voltages add up. Remember, these are voltages, not potentials. They're potential differences. The V's add up. Okay. And therefore, the resistance adds up in series, meaning I can replace this resistor, or these two resistors, this pair of resistors, with a single resistance that has the sum of the two original resistors, and the circuit would function the same way. So if this was the same V tot, we can replace this with Req, where Req is R1 plus R2. So we are simplifying our circuit, kind of like simplifying fractions. Whoa, tumbling down to the ground. After coming back to the ground at 0 volts, the battery will push you up again, lift you up to the 3rd floor, and then you can go down with this cyclical ride forever. Okay, so that means R12 should be R1 plus 2, which is, for me it was 5 plus 10. Depending on how you oriented your resistors. 2 plus 3 would be 10 plus 20, which is, oh, whoops, 10 plus 20, oh no. Which is equal to 30. And 1, 2, 3 would be 35. That should be the same for everyone. Current through the battery is the total current, which is also the same as everyone else. And power total should be I total times V total. Okay. And yes, you can use light bulbs to replace, so you can do the conceptual questions in our worksheet. Oh, whoa. Let's attach it. How do I do that? There we go. Okay, and basically the brightness is in this model is indicated by those little yellow lines you see. If the yellow lines are longer, that means it's brighter. Whoa. Whoa. Okay. So you can do the conceptual questions using light bulbs instead of resistors. Okay. Always draw the current flow diagram when you're analyzing circuits. So the first thing you should do is say that current is coming out of the plus, and then it goes through the resistors, and then goes back into the battery. Okay, this will be kind of your work, your proof. With only one loop here, one pathway, the current must be the same. All right. Boom. We're going to skip these. This is like honors physics stuff. We'll go to resistors in parallel. Resistors in parallel. You'll see that the resistors in parallel setup, the top and bottom of each resistor is actually connected directly to the battery, the top and bottom of the battery. Therefore, the potential difference across each resistor is the same because they're connected to the same points in space, if you will, the same potential points. So whether I drew it sideways or right side up or vertically or horizontally, it doesn't really matter. So let's go and do a simple model, a 2 resistor model first, and then we'll do the 3 resistor model. Here's our battery again, big line, small line. Let's go and draw 2 resistors in parallel. Here is resistor number 1, R1, and here is resistor number 2 in parallel to resistor number 1, R2. So R1 and R2 are parallel. Whoa. Parallel has nothing to do with parallel lines. It has everything to do with how the current splits and recombines. So again, now we do our current flow diagram. Comes out of the positive. Once you get to here, you have 2 choices. Goes down this way. Goes down this way. And then that same current will eventually come back and meet up so that it can go to the bottom of the battery. Now, will this stream ever go upwards instead? No, it doesn't. That's because once you've reached this point here, any point around this region, let's call this a node. Ooh, nodes. And any point on this node has the same potential because that part of the circuit is connected to the bottom of the battery. Okay. Therefore, imagine this being the ground. So whether you took the first set of staircase or the second set of staircase doesn't really matter. You've basically reached the ground, and you still, you can't just go up. You got to take the elevator to go up, apparently, in this model. So you have to go back to the end of the battery. And it is this fact that after splitting up and recombining, we have these two resistors as being parallel resistors. This point, it's called a junction. Junction, junction, what's your function? It splits up and recombines current. This is also a junction. Splits and combines current. All right. So if I now draw the elevator model, we have an elevator that takes us up like so. The first set of staircases will drop me straight to the ground, R1. The second set may be, a different set of staircases, like baby steps or so. Baby steps. Boo, boo. It's a different pathway, a scenic route, but eventually you'll get to the bottom. Oh, that's not R1, it's R2. And remember, each charge, each person, can only take one staircase at a time. It doesn't take both. So one of these charges will go through, and perhaps the next one might take the other path. All right. Here we go. And it turns out that based on the type of resistance you have, based on the values of the resistors, different amount of charges will flow through each. Okay, current always takes the path of least resistance, so the path that has more resistance will receive less current, and the path that has less resistance will receive more current, such that the products are always equal. Why wouldn't the charges take the... yeah, they do. It's just more will take the least resistance path, and some... It's kind of like, let's say everyone's driving on the freeway, and there's a huge jam, right? Some people will be looking at their Google Maps, and sometimes Google gives you an automatic notification, gives you an alternative route to take a different pathway that will save you some time. But not everyone checks their phone, so some people will miss that notification and continue on through the regular path. So yes, some sucker will take the longer path, while some other people will take the shorter path. So in essence, what is happening, remember, it's not that each charge has really a choice. It's all of these charges lined up next to each other, and you're getting a push. So when you get a push, you have two pathways. Imagine playing Plinko. If you don't know what Plinko is, consider watching The Price is Right. There's these little slots where these discs can fall into. And so if you're given a push, this, a lot of the times, this might go through one way, whereas the other times it might go through the other way. Imagine the path with less resistance being a wider path, so more discs, essentially at a far higher chance rate, will fall into the path with the bigger streets, or the bigger, imagine having a freeway with like 8 lanes, whereas this one only has like a single lane, so only a few cars will fit. Okay, but just because it has one lane doesn't mean no one will take it. right? At the end of the day, everyone will take every path. You're all, going through whatever destination your home is, which is the bottom of the battery. It's just with a bigger freeway, we can send in more cars per second, and so the path with less resistance will send in more charges per second. And it's a relationship, it's a ratio. Again, with less resistance, more current, more resistance, less current. Now, if you have infinite resistance, then no current goes through, and all the current must go through any other path that you have. If you have zero resistance, then all the current will go through that zero resistance path, and nothing will go through the other path. And we'll talk about that later. It's called a short circuit. Okay. All right, so V1 is equal to I1 times R1, which must also equal V2, which is I2 times R2. Okay, so in your second part, V1 equals V2 equals V3 V12. Now, how do you actually measure V12? Well, if you want to measure it, you want to touch the top of number 1 and the bottom of number 2. So that's V12. Okay, and if you do that, then again you should get the same. That's because every point in this node is the same potential, and every point in this node is the same potential. And therefore, you're basically touching 2 points in space that have the same electric potential value. Recall that electric potential was the kq over r thing we did for single charges. So now we have a full potential value based on all the charges in space for that point. All right. Now, finally, we want to figure out how to get the equivalent resistance. It turns out that instead of adding linearly across like series resistors, for parallel resistors, REQ, actually 1 over REQ is equal to 1 over R1 plus 1 over R2 dot dot dot. Basically, you're adding the inverses. Now, if you invert this, the sum or the total resistance will be 1 over R1 plus 1 over R2 plus 1 over R3 dot 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 dot. Okay. So if you have 3 or more, you should use this format: 1 over 1 over, the 1 over 1 over. However, if you only have 2 resistors, there is a shortcut. As you can see, if I had 2 resistors only, we'll call this rec for 2, rec parallel for 2, and only use this for 2 resistors. For 2, it would be rec is equal to 1 over R1. Oh, I forgot the 1 over again. 1 over 1 over plus 1 over R2. And what we could do is find common denominators. 1 over, this is R1, R2 times R2 plus 1 times R1 over R1 times R2. So, common denominators. Multiplying the first one by R2 over R2, multiplying the second one with R1 over R1. This gives us 1 over R1, let's try that again. 1 over R1 plus R2 over R1 times R2, and by inverting this, we get the product over the sum. So this is rec for 2. Product over sum. So a lot of times you might have 2 resistors in question and they're in parallel. You know for a fact they're in parallel. Just do product over sum and that'll get you the total resistance of that pair. Okay? Right, it doesn't end there. We want to look for patterns. So let's say we had a battery. Resistor 1 is 100 ohms. Resistor 2 is also 100 ohms. Okay, are these two parallel? Yes, they are. Remember, parallel means once you split the current, these two currents, after going through their resistors, after going through R1 and after this one going through R2, they have to combine again. And if they do, then they are parallel. If there's a third resistor in the way, then this one is no longer the same, and therefore they're no longer in parallel. And we'll do combination circuits tomorrow. But for today, we're going to keep it simple. Okay, so what's the rec for 2 with 100 and 100? Well, if I did product over sum, we get 100 times 100 over 100 plus 100, which is 100 times 100 is 10,000. 10,000 over 200, that's 50. Whoa, interesting. What if I had 3 resistors in parallel? Let's draw 3 resistors in parallel. Wait a minute, are these parallel? What's going on? Whoa, they're weird. Yeah, you can draw it basically in any shape as long as when you split the current. So here's our junction. We're going to split it. Some of it goes this way, some of it goes that way, some of it goes that way. Notice how after going through each individual resistor, this is I1 going through resistor 1. This is I2 going through resistor 2. This is I3 going through resistor 3. Okay, after going through, they combine into a node. Here's a node. How do I know this is a node? That's because this, and this, at any point along this region is essentially connected to the bottom of the battery, and therefore it must have the same potential. Okay? So these 3 are parallel. Let's say they're all 100s. 100, 100, 100, 100 what? 100 ohms. Omega. So what is rec for 3? How do you do rec for 3? Our formula product over sum is only rec for 2. If you want to derive, you can by finding common denominators, but that takes way too long. So just do the original formula. If you have 3 or more, just do the original formula, and that is rec is equal to 1 over 1 over 1 over 1 over 100 plus 1 over 100 plus 1 over 100, which is 1 over 3 100ths, and the inverse of 3 100ths is 100 over 3, which is 33.33333 ohms. Do you see a pattern? Well, maybe we should try 4. Let's try 4. I'm running out of shapes. Whoa. Okay, that's way too weird. Let's try it. Let's try it like this. Actually, I could have drawn it like that. Doesn't matter. But we're going to draw it like this. Notice how it'll split, go this way, go that way. Some of it will go this way, some of it will go this way. After going through, we're now on the ground. So eventually they'll all combine into one stream again and going into the battery. Okay, if I have 4 100s, we get 1 over 100 plus 1 over 100 plus 1 over 100 plus 1 over 100, which is 1 over 4 100s, and it's 100 over, nope, over 4, which is 25. So if you have the same resistors, same resistors in parallel, you're basically, cutting it in half or a third or a fourth. If you have 10 100s, then it'll be 1/10, and the total will be 10. Notice how the rec decreases when you're in parallel. The more parallel paths you have, the less resistance overall you have in the system. Therefore, the more current you'll have in the system. The total current goes up because the total resistance keeps going down. Remember, current, if I use Ohm's law, must be equal to the total voltage divided by the total resistance. And so as R goes down, I must be going up. And this is the opposite to our series circuit. Remember, I total, again, is still V total over rec. But we know that rec increases. The more R's you add in series, remember series, I wrote it in the parallel section. Let me try that again. Here we go. In series, rec is the sum, so rec goes up, and if rec goes up, I must be going down. It's like the circuit has more area almost. Yeah, it has more lanes. We're trying to add lanes to the 5 freeway so we can get more cars to go through per second. And so by adding more resistors, even though a resistor adds resistance, technically, it's a resistor, you're technically still adding another pathway for the current or the charges to flow. And therefore, even though there's a resistor, it's still another lane, and therefore some cars will take it, and therefore you're going to get more flow through the entire circuit as a whole. The extra amount of current you get in comparison, as we'll find out later, gets put into the new pathway, which is really cool. So let's take a look. All right, should we do 100 volts? 100 volts. Let's compare two circuits now. It's all about comparisons. Yeah, so because series has 1 lane, these have like 4 lanes, so there's more flow. Yes, very good. So let's compare two circuits, one with 2 resistors and one with 3 resistors. I'll draw it normal. Okay, they're all 100 volts, 100 ohms, etc. Okay, so everything is 100. And then we'll do another one after that. If you're ahead of the game, go ahead and try it. We'll do 150. Okay. All right. For this, we know that the total resistance is actually 100 times 100 over 100 plus 100. So the total resistance is 50. Rec equals 50. Okay. If rec equals 50, then I total must be equal to V total over rec, which is 100 volts over 50 ohms, which is 2 amps. I'm going to ignore sig-figs today. Actually, technically I didn't. Everything is 1 sig-fig, but ideally I want 3 sig-figs and everything. What does this 2 mean? Well, the current that comes out of here is 2 amps. And that 2 amp keeps on going until it hits this junction here. Once it hits this junction, it's going to split up. The amount of current that goes into this junction currently is currently is 2 amps, right? But it splits. Since both pathways have the same amount of resistance, yes, thank you, Owen. Uh, as 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 both pathways have the same resistance, okay, it splits evenly, 50% and 50%, such that 1 amp goes one way. Oops, this is 1 amp, and 1 amp goes through the other way. Okay. Now you might be thinking, wait, there's more wire and stuff, and why is it 1 and 1? Well, the wires are ideal, so they don't actually add anything to the system. It's just a perfect pathway. Okay. And then these two 1 amps will eventually, they don't get used up or destroyed. You can't destroy the charges. They'll combine again at this junction, at the bottom here, and thus giving you your 2 amps back that go into the battery. If you have 2 amps coming out of the battery, you're going to get 2 amps going into the battery. For every charge that comes out, there must be another charge that's going in at the bottom side. Okay, what is V1 equal to? Well, V1 should be I1 times R1. Okay, I1 is 1 amp, R1 is 100 ohms, and this gives us 100 volts. Well, of course, it's the same as the battery itself. Remember, V1 equals V2 equals V3, etc. equals V total. All right, how is this one different? Well, at this junction, we split. What we could do, when you have a node like this, what you could do is pinch the node into a point. Squeeze it, the squeeze theorem. Squeeze theorem for circuits, not for integrals or whatever you guys do in calculus. Squeeze the node. Into a point. This is also a node, so we're going to go ahead and squeeze it into a point. So instead of drawing it this way, we could draw it like so. Here's our battery. We squeezed our node into a point, into a singular junction, so that leaves our resistors kind of bendy like this. And voila, these two are the same. These two circuits are the same. Remember, all the values are 100. What is rec? Chat, what is rec? Well, rec would be, again, this is rec for 3. We already did that. Very good. 33.333. Now, when you write it, of course, try to use 3 sig-figs or whatever. When you're calculating, leave it alone, or could just say 100 over 3, so that your values can be as consistent later on down the road. The amount of current total must be equal to the total voltage over this rec. So the total voltage is 100. The rec is 100 over 3. And so 100 divided by 100 over 3 is just 3. Very good, Shiraz. Oh, no, it's not 3 volts, it's 3 amps. So that means now we are sending out 3 amps of current. That means 3 amps of current must be coming back into the battery. Okay. Notice how by creating an extra pathway, we have increased the total current in the system because our total resistance decreased. Okay. But how do they split up? Well, again, since they're all the same, where each is going to get 1 amp of current. Well, this is we are assuming that we're always adding the same type of resistor. So we'll start adding different values and we'll get a different amount of increase. But yes, essentially it increases. And it's also how you add the resistance into the system also matters. because circuits don't always have to be series or parallel. They can be series and parallel at the same time, or they can be neither of the two, which are complex circuits. So we have far more things to learn down the road, but I like that you're looking for patterns. So good job, wireless high five, for looking for patterns. All right, so we get more current. Notice how before we got 2 amps, now we get this 3 amps here. That extra 1 amp is essentially going through the extra pathway you created. Okay, so we'll keep that thought. We'll do this next one, and we'll come back. For those of you who are ahead of the game, go ahead and keep going. The next one is 100, 150. If you're ahead of the curve, go ahead and do that one. 100, 150. But we're going to focus on this second one. Oh, sorry, third one. How is this different? Well, our rec is different. What is rec? Oh, look, it's 2 resistors in parallel. We can use rec for 2. 100 times 50 over 150. $100 times 50 over 150. Chat, what is it? $5,000 over 150? No. 100 times 50 over 150. Wait, what are we looking for? We're looking for rec. Yeah, there you go. 33.233. Wait a minute, this has the same resistance as this one here. Whoa, how did that happen? Here comes these APC kids. Bam. Get your own account. Use your own name. We just dropped the ban hammer today. Alright. How did this happen? Well, patterns. The rec for 2 equation can always be used for resistors that are parallel to each other. Okay, even though all 3 are parallel here. Ooh, this is pretty messy. So here's our resistor. Okay, notice how even though all 3 are parallel, just because all 3 are parallel doesn't mean we have to do all 3 at once. Okay, we can ignore this third one for now and just look at the first 2 resistors. We can say that the first 2 resistors are parallel to each other. R1 is parallel to R2. R1 is parallel to R2. And since R1 and R2 are parallel, we can do rec for 2 and say that these 2 can combine. 100 gives you half, which is 50. These 2 can combine to give you a 50 ohm. And now we bring in the third 100 ohm, and notice how we have the same circuit. We have the same circuit. Whoa. Now how does it split? Okay, remember, more current will go through the 50, less current will go through the 100. It's a 2-to-1 ratio in resistance, therefore it's a 1-to-2 ratio in current. Okay. All right. For now, we're going to use the voltages to find the current, and later I'll show you how the current splitter rule works, where you can find the current outright. But for today, we're just going to say that because it's parallel, V total must equal V1 must equal V2. So this is V1, V2. Therefore, I1 must equal V1 over R1, which is 100 volts over resistor 1, which is 100 ohms, this gives us 1 amp. So we know that 1 amp goes down through the 100 ohm resistor. Okay. What was our total current? Total current was 3 in the last one, so it better be 3. Let's take a look. I2 is equal to V2 over R2. V2 is the same voltage, so 100 volts, because it's touching the top and bottom of the battery as well. And resistance 2 is 50 only, so that gives us 2 amps. Whoa! Half the resistance, twice the current. Yay, patterns. Okay. Remember, we split this up. 1 amp goes through here, and 2 amps goes through the scenic route, I guess. Technically, it's this path of least resistance. So how much actually went in? Ooh, it's too big. Well, 3 amps went in. That's because the total current was always 3. The total current, I total, must be V total over rec, which is 100 volts over the 33.33, which is 3 amps. Yes. So we have our current splitting up. Smaller resistor, more current, bigger resistor, less current. Okay. And how about this one? This one is actually different. 100, 150. Rec is 1 over 100. 1 over 100. That's 1 over 150. Uh-oh. Now 1 over 150 is the same as 2 over 100, right? Okay. So this gives us 4. So 1/4. Rec is 25. Okay. If rec is 25, then I total must be 100 volts, which is the battery, divided by the 25 ohms, which is 4 amps. Whoa, 4 amps now come out of here. Okay, and they split up. How do they split up? Again, V1 is 100, V2 is 100, V3 is also 100, because they're all parallel. 100 over 100, 1 amp goes this way. 1 amp goes this way. And the leftover, the 2 amps, goes through the 50 ohm resistor. Okay. So we have 4 circuits. Let's compare them. The first one, we had 2 100s. The total current was 2 amps, and it split up evenly, 1 and 1. Okay. By adding a third resistor, we increased the amount of current in the system, and the extra 1 amp went through the third path. By adding a third resistor that is smaller, in 50 ohms, we added 2 extra amps, but both extra amperages, both extra amps went through that third pathway. Okay? It did not actually change the amount of current that went through the first 2 pathways. Anytime you create a new pathway, the extra amount will just go through the new path. Alright, that's it for parallel today. Thank you for tuning in. I'll see you next time.